So now that we've talked about the internal components of a computer, we're going to venture off and dissect them a little bit more. Now, a couple of the main things we discussed were the CPU as well as the hard disk drive and RAM. And two aspects of those can be pretty engaging when we're looking at buying a new computer. In particular, how fast is the CPU and how much data can the RAM and the hard drive actually hold. So to really answer that question, we need to understand what those terms actually mean. So that's what we're looking at today. First of all, let's talk about the speed of a CPU. When somebody says, hey, how fast is your computer? Or what's the speed of your computer? What's the clock speed of your computer? What they're talking about is the frequency, which really boils down to the number of operations the CPU performs per second. When we say operations, we just mean the basic operations, which are additions or comparisons. Again, that's all a CPU really does. It adds and it compares data. So we want to know, well, how many times can it do that per second? The unit that is 1 hertz. So 1 hertz means 1 operation per second. This little table below breaks down the multipliers of those, the various units from that standard measurement. So 1 hertz is your basic. When you have a kilohertz, that's 1,000 hertz. Now you've heard the term kilo before, whether that's kilogram, which is 1,000 grams, or kilometer, which is 1,000 meters. Kilo always means 1,000. So a kilohertz is 1,000 hertz. There's also megahertz, which is 1 million hertz, and gigahertz, which is 1 billion. So whenever you hear these terms, kilo, which is 1,000, mega is 1,000,000, giga is 1,000,000,000, that applies in all units when they apply to any form of measurement. So keep these in mind going forward. So that means if something has a frequency of a gigahertz, that means that it performs 1 billion operations per second, 1 billion additions or comparisons. That seems like a lot, and it really is, except it's working with very small points of data, bits, those ones and zeros. So as much as it seems big, we still need to be able to do as much of that as possible. So in the late 90s, CPUs ran at approximately 66 megahertz. This is actually a computer that I worked on when I was your age in my grade 11 programming class. Actually, it was 33 megahertz, and the only way you could get it up to 66 megahertz is if you push that big button on the front that said turbo. Of course, when you did that, it made the computer sound like it was a jet landing, but, that's the way it goes. Today's computers typically run at about 3.2 gigahertz. So we got 66 megahertz, so million operations per second, versus 3.2 billion operations per second. That's a huge difference. It's about 48 times faster in just a few years. That's not too bad of an increase. I like that. So let's keep going on that speed of the CPU. So as I said, 1 gigahertz represents 1 billion operations per second, and 3.2 gigahertz is 3.2 times bigger, so you just multiply. So that's 3.2 billion operations per second. But the thing is, modern computers typically don't just have one CPU in them. They really have multiple CPUs called cores on a single chip. So that core, that CPU may be cut in half, and it would have 2 CPUs on either side. We call that a dual core. Dual means 2. Sometimes it's cut into quarters, so that is a quad core, four cores. And then sometimes there's 8. You have an octo core. And it really depends on what you're running. If you're running an i5 Intel processor, those are usually dual cores. i7s are usually quad cores. So that means how many CPUs are on that chip at once. So how does that affect the calculations? Well, really, every CPU can work independently. So when you see a CPU that is 2.8 gigahertz and it's a quad core, that means that you have 4 CPUs rocking 2.8 gigahertz. So that means you have 4 times 2.8, which is 11.2 gigahertz for the full frequency of the CPU, or 11.2 billion operations per second. It's a ton. Now that being said, that's the number on paper. In reality, the number is actually a little bit smaller than that because it takes time for data to transfer and things like that. So, but on paper, in theory, 11.2 gigahertz or 11.2 billion operations per second. So that's how we know how fast our computers are. There are other ways that engineers have come up with to speed up computers other than just straight frequency. They've done things like hyper-threading and stuff like that, which allow more things to happen on the CPU simultaneously, that kind of stuff. But that's another course. So let's talk about file sizes now. When you're buying more RAM or a flash drive or hard disk drives or things like that, or a solid state drive, you need to understand what all those measurement data actually mean. In reality, we know what the smallest form of data is. That's a single bit. Okay? Now we're going to keep this in mind, and we're going to scale it up. And I want you to think of that bit almost like a basic unit of measure. So like a millimeter. Now, a millimeter is the base unit of measure that we typically use. And then if we put 10 millimeters together, we get a centimeter. If we put 100 centimeters together, we get a meter. If we put 1,000 meters together, we get a kilometer, and so on and so forth. So they're all just scaling by a number. Now, we're going to use a bit as our base unit of measure. Well, there are 8 bits in a byte. And now from here, we're going to go up to kilo, mega, giga, and tera. Now we remember from our earlier lessons that kilo means 1,000, mega means 1,000,000, giga means 1,000,000,000, and tera means 1,000,000,000,000. Now, if you look at this line here, it says your typical hard disk drive that you buy in a desktop computer nowadays is usually around a terabyte big. So that tells me that in terms of size, it's approximately 1,000,000,000,000 bytes. Approximately. But we can actually calculate how many it specifically is. Okay, now how do we do that? Well, we measure this, we multiply up by this factor every time. So just like a meter is the equivalent of 100 centimeters, if I wanted to know how many centimeters are in a kilometer, I would first say, okay, well, there's 100 centimeters in that meter, and then there's 1,000 meters. So I'd multiply by 100 to get to the meter, and then I'd multiply by 1,000 to get to the kilometer. So I'm doing multiple steps of multiplication to get to the desired unit of measure. It's the same thing here. If I know how many I have, let's say I have 5 bytes of data, and I want to know how many megabytes that is, well, I got to do either multiply or divide to get to the right unit, depending on whether I'm going down this chain or whether I'm going up that chain. That brings us to our next point. Conversions between the size. So converting between the data sizes is as simple as converting between any two forms of measure, as I just described with millimeters to kilometers, or centimeters to kilometers. So just remember the table on the right here. So if you can remember this order, bits, bytes, kilobytes, megabytes, gigabytes, terabytes, if you can remember that order, because it goes from the smallest up to the biggest. There's actually bigger sizes in this, of course, petabyte, xenobyte, yottabyte, and things like that. But we're not going to get into that right now. Okay? So what this chart is telling us is that anytime we're going up the chart, we're going to multiply. Anytime we're going down the chart, we're going to divide. So if you can remember the chart, and up means multiply, down means divide, down divide, down divide, you will get it every single time. But remember to take your time and do it in steps. Don't try and do it all in one pump on the calculator, because you're going to make a mistake. You're going to miss a factor, you're going to type something in wrong, and that's just going to cause you more headaches. Do it one step at a time. So just remember the table on the right. If you're moving up, you're going to multiply. If you're moving down, you're going to divide. So how much do you actually multiply or divide by? Well, we know that there are 8 bits in a byte. That means if I want to go from bits to bytes and I'm going down, I'm going to divide by 8 because there's 8 bits in a byte. If I know how many bytes I have and I want to get to bits, I'm going to multiply by 8 because, again, there's 8 bits in a byte. So if I have 5 bytes, for example, I'm going to say 5 times 8. Well, that's 40 bits. Alternatively, if I have 40 bits and I want to know how many bytes that is, I would say 40 divided by 8. And I'd say, well, I have 5 bytes. So let's keep this in mind going forward. Now, what about these ones? All of these ones are factors of 1,024. So anytime you're going past here, you're always dividing by 1,024. Anywhere you're going up here, you're multiplying by 1,024. The only time it's 8 is when you're going between bits and bytes. That's the exception to the rule. Everything else is 1,024. So let's look at a quick little example. How many bits are in 37 megabytes? 37 megabytes is not very much, so let's do it real quick. So we start with 37 megabytes, and we're going to take it one step at a time. And I want to say, well, I'm at megabytes, and I'm trying to get to bits, so I'm going to take it one step at a time. I'm going to say, well, let's go from megabytes to kilobytes. So I say 37 megabytes is how many kilobytes? Well, I'm going up, so I'm multiplying, and I'm not up here yet, so I'm multiplying by 1,024. So 37 times 1,024 is going to give me 37,888 kilobytes. Okay, great. I'm still not at bits yet, so I need to take another step. So we're going to go from kilobytes to bytes, which is this next step. That should be a kilobyte. I will fix that before you guys see that. So that should be 37,888 kilobytes. I apologize. So we're going to take that, and then we're going to multiply by 1,024 again because we haven't crossed that threshold. And we're going to get 38,797,312 bytes. We're still not done because we got to get to bits. And now we're finally at the stage where it's always a factor of 8. So in this one, we're going to be multiplying by 8. And we end up with 310,378,496 bits. So in 37 megabytes, which is nothing, we have over 300 million bits. So you can see that the numbers get pretty huge. Most of the time, your regular calculator is not going to work with that. So I recommend you pulling up the Windows calculator. All right, and this one can go for massive amounts of digits. All right, almost done. So one more quick example. How big is a USB flash drive that holds 34 trillion? Am I right there? Let's see, thousands, million, billion. 34,359,738,368 bits. I want to know how many or how big that flash drive is. So we start at bits, which is where we're at, and we're going to take it one step at a time. Bits to bytes. So since we're in that range of that table here, up here, we're going by 8. And since we're going down the chain, we are dividing. So I have this massive number of 34 billion and a bit, and we're going to divide that by 8, and we end up with 4 billion and a bit. Now we go another step. Now we're going to kilobytes. But we've passed the bits bytes thing, so now everything's by 1,024. So we have 4 billion divided by 1,024. Now we're at a little bit more than 4 million. Great. So we keep going. 4 million kilobytes is how many megabytes? Divide by 1,024 again. We have 4,096 megabytes. Okay, we're still not done yet. We can keep going with this. 4,096 megabytes is how many gigabytes? Oh, it's exactly 4. I'd be lying if I didn't say I picked this number specifically. You're not always going to get a perfect number. This one was. So that came out to exactly 4 gigabytes. So our flash drive is a 4 gigabyte flash drive to the bit. So that means that there's over 34 billion bits on a very tiny little 4 gigabyte flash drive. That's crazy. That's a lot of ones and zeros. So that's it for conversions of memory sizes and calculations of frequencies.